Hello everyone, this is lecture 5 on extensions of Banach contraction principle. Now the further extensions of Banach fixed point theory. This was given by Garethe. For this he first defined a class S, which is a class of those functions alpha going from R positive set to the semi-open interval 0, 1 closed from 0 and 1 from open, which satisfy this simple condition that if you consider any sequence of real numbers and you apply this function, this mapping, if this thing goes to 1, then this implies that the sequence is a null sequence, means this Tn goes to 0 as n goes to infinity. So this is a class of all such functions which satisfy this simple condition. Now the theorem says let MD be a complete metric space, let T be a mapping going from M to M, and suppose there exists alpha belonging to class S. Alpha belonging to class S means alpha is a mapping going from R positive to semi-open close interval 0, 1 such that alpha of Tn going to 1 implies Tn is going to 0, where Tn is any sequence of real numbers, right? So T is a self mapping such that there exists some alpha belonging to S, and for each xy T satisfying this inequality. This is contractive condition. Here distance of Tx Ty will be less than equal to alpha times distance of xy into distance of xy. So here alpha of d of xy is a mapping, is a function, right, going from R positive to 0, 1. So since here we consider a function, and in Banach contraction principle there is some constant, so that's why this is an extension of Banach contraction principle, right? So then T has a unique fixed point in M, and any sequence converging to this fixed point, this will exist for each x belonging to M, right? So what is given to us? M is complete, T is a self mapping satisfying this inequality, then T has a unique fixed point in M, and T is also continuous because using this contractive condition, whenever the distance between this is very small, then the distance of this is also small because this is number which is strictly less than 1. So this is continuous also. So T is a self mapping satisfying this inequality. For this proof, we first consider any point of the set M, right? We apply the mapping T, we get a new point x1. So 2 times applying this mapping on the point x, we get x2, and so on. So xn is the nth iterate of T at point x. In the first step, we will show that the distance of xn and xn plus 1, means distance between two consecutive points, will be 0, as we are going to tail, you can say, and going to infinity, right? So now just see how to prove this. First we consider d of t of xn comma xn plus 1. What is our t of xn? This is xn plus 1, right? What is our t of xn plus 1? This is xn plus 2. The same way, x1 is tx, x2 is t of x1, x3 is t of x2. So t of xn will be xn plus 1, t of xn plus 1 will be xn plus 2. Now by given condition, it will be less than equal to alpha times distance of xn, xn plus 1 into distance of xn, xn plus 1, right? So now you can take this number, this positive real number, to this side. So you get this divided by this is less than equal to alpha times this. Now since our alpha belongs to class S and the codomain is this interval, so it means the value of this should be strictly less than 1. So this implies that this number is less than equal to this number. So which implies this sequence is decreasing sequence. So this is monotonically decreasing. So by the theorem of monotonic decreasing sequence, if we have a sequence of real numbers which is monotonically decreasing, and if it is bounded from below, then this sequence is always convergent. Now just say this is always bounded below by 0 number, because both these numbers are positive real numbers, so this is always greater than equals to 0. So this sequence is monotonic decreasing, this is sequence is bounded below, so this should be convergent. So say it converges to the number r, where r is any positive number, right? First we assume that this r is non-zero. Actually we want to show that this r is 0, but we, in contrary, we assume that this r is non-zero. So if this r is non-zero, by the condition this, which I have already discussed in the previous slide, right? The distance of this divided by this is will be less than equal to alpha times this. Since it is true for every n, so it is true for limit also, so we take limit to both sides, right? So what will be the limit of this sequence? It is nothing but r whenever our n is going to infinity, right? This number is r, similarly this is also r, so r will be cancelled out, you get 1. So 1 is less than equal to the limit of n going to infinity alpha times this, right? But since our alpha, it belongs to class S, so this value should be strictly less than 1, right? So this is true for each n, and this should be strictly less than 1. So we get uh, this limit is greater than equals to 1, which is the contradiction, right? Because if the inner number it goes to if this goes to 1, right, then the inner should goes to 0. So we get contradiction because we assume that this is non-zero. So in both cases we get contradiction, so our position is wrong. It means this should be 0. Okay, so this is the proof of the first step. Now in the second step we will show that this sequence is a Cauchy sequence. So for this we consider the distance of xn and xm, and we suppose that the limit of this whenever mn going to infinity, this is strictly greater than 0, it is not 0. In actual we want to prove that this is going to 0, but we assume that this is strictly greater than 0. Now using the triangles inequality, add two numbers over here, one is xn plus 1 and xn plus 1, right? So we get this inequality. Now on the second number you apply the contractive type condition which is given to us in this theorem, so it should be a less than equal to alpha times this into this, right? Rest terms are same. Now you can take this number to be this side, so this will be common out and you get this inequality. Again distance of this will be less than equal to, you can take this number to be this side, this, right? So now just see, as this number is positive and finite number, and these terms are going to 0 by the step 1, okay, and this is strictly greater than 0, these numbers are greater than going to 0, and this number is strictly greater than 0. It means this number, it should goes to infinity, so 1 over this number this number, it should goes to infinity. So if this goes to infinity, means the denominator, it should goes to 0, right? So if the denominator is going to 0, right, it means the alpha of this thing is going to 1 as nm going to infinity. By the given condition that this alpha belonging to class S, whenever this sequence is going to 1, the inner sequence will go to 0. So which is contradiction to assumption that this is strictly greater than 0, right? So that means our position is wrong, it should be 0. So this implies the sequence is a Cauchy sequence. Further, we know that this space is complete. So if by the given hypothesis, if this space is complete, then this Cauchy sequence should be convergent. So now just see, x to the power n can be written as t to the power n of x. So this sequence is basically Cauchy sequence. So it should be convergent. Let it be converging to z as n goes to infinity. So by the contractive condition, since t is continuous, we can take limit to be inside. So this will be t of xn minus 1, you can say, or xn 1 and the same thing, because our n is going to infinity. So what is the value of this? This is nothing but z, because our sequence is converging to z. So t of z is z. This implies z is a fixed point of t. And using the same concept, we can easily prove that this fixed point is unique, as we have already done in Banach contraction principle. So therefore there exists unique fixed point of t. Now the next result. For the next result, we define a new collection of monotone decreasing mappings. Call this collection as S dash. So S dash denote the collection of all the monotonic decreasing mappings going from R positive to R positive, for which this condition holds that psi of R is strictly less than R. It is positive, strictly greater than 0. So this mapping is a mapping which is strictly greater than 0, and this is strictly less than the number R itself inside, for which this is continuous from right side, right? Means if we consider Rj going to R from right side, then psi of Rj is going to psi of R. And this is the extension which is given by Browder, right? So this is extension due to Browder. So in this case, he considered this class S dash. So again, let MD be a bounded complete metric space and T be a mapping which is continuous, and suppose there exists psi belonging to S dash, for which this condition hold that for each xy belonging to M, the mapping T satisfies this inequality, then T has a unique fixed point Z, and again the sequence converging to the same Z for each x belonging to M. This theorem is a special case of the previous theorem. So for this we introduce the function psi bar going from R positive, you can say R positive, to the interval 0 1 by setting psi bar 0 is 0 and psi bar t is psi t by t for t greater than 0. Now just see, our psi t is a function which is in class S dash, and this mapping satisfying that psi t is strictly less than t, and it is greater than 0, strictly greater than 0 and strictly less than t. So clearly psi t by t, it should be strictly less than 1, and it should be strictly greater than 0 also. So that's why we define the value at 0. We define psi bar 0 is 0, and for rest points we define psi bar t as psi t by t. Clearly this value is strictly less than 1, so its range will be this interval, right? So we need to show that this psi bar t is a member of class S, right? The class S is a collection of all those mappings which are going from r positive to 0 1, such that uh, if we consider any sequence Tn, then psi bar Tn going to 1 implies Tn going to 0. So we need to show main this condition. Suppose that we consider any Tn such that psi bar of Tn is going to 1, right? Then this must be bounded. Now why this sequence Tn? If this is not bounded, then what will be the limit infimum of psi bar Tn? It is nothing but psi of Tn by Tn. So if it is not bounded, means it is infinity or minus infinity, whatever. So whenever you take the limit, it will goes to 0. Okay, so we get contradiction because this number is strictly less than, तो ये इससे छोटा है. So after applying the limit, the denominator will be very very large. So that's why this limit will be 0, right? So which is a contradiction because this limit is 1. So therefore this sequence should be bounded. Now we choose a subsequence and we assume that that subsequence is going to T naught. So Tn is going to T naught. We further assume that either this Tn is monotonically increasing going to T naught or it is decreasing going to T naught, right? Now since psi is a continuous from right side, so Tn monotonic decreasing going to T naught will lead psi of Tn is nothing but T naught because it is continuous from right side. So whenever our Tn is going to T naught from right side, right, and since it is decreasing, so psi of T naught will be nothing but T naught. And since psi r is strictly less than r for any r greater than 0, so it means T naught should be 0, right? So our Tn is going to 0. So Tn is a monotonic decreasing which is going to 0. So the here T naught is 0. Now if we consider Tn is monotonically increasing going to T naught, then by monotonicity of psi of T naught by Tn, basically psi bar of Tn, it is going to 1. So if we substitute the value of psi bar, it is nothing but psi of Tn upon Tn, and by the monotonicity of psi, since it is monotonically increasing, so psi of Tn should be less than equal to psi of T naught, right? So we get this thing. And from here, this number is greater than equals to 1 for each n, right? For each n, and our Tn is also monotonically increasing going to T naught. So what we get the value of this at T naught also, it is greater than equals to 1. But that is a contradiction, right? Because this value psi of T naught upon T naught, it should be strictly less than 1. That then we get psi of T naught is strictly less than T naught. So we get contradiction over here. So this means again T naught should be 0. So we get a convergent subsequence of original sequence Tn, right, which converging to 0. So we get sequence Tn which is going to 0 implies that psi bar, it belongs to class S. And since d of tx dy is less than equal to psi of dx dy by the given condition, given hypothesis, now we can substitute the value of psi t. It will be psi bar into t. So psi bar of d of xy into d of xy. This for all xy belonging to M. And this is a condition given in the previous theorem. So this thing hold for each xy belonging to M. Also over this psi bar, it belongs to class S and the space is complete. So by using the previous theorem, the mapping T has unique fixed point.